Great. So today I'm excited to have Charles with us to present his own paper, Implicit Self-Regularization in Deep Neural Networks. Of course, before we hand the baton over to Charles, we'll just have a few remarks here, and then we'll dive into kind of an open mic community discussion. And then Charles will have the bulk of the hour to walk us through his presentation. A few quick words about upcoming meetups. In March, so we've got two meetups in addition to the study group. There's an EMEA meetup, which basically meets evenings in Europe, and an Americas meetup, which meets evenings in the Americas. The Americas one tends to be the middle of the month, and the EMEA one tends to be beginning of the month. For the next EMEA meetup, Kai, who hosts that meetup, is going to be doing a special, kind of a tech special. He has put together some Docker containers for data science and has written about those and shared those widely, particularly with in the group of folks that are working through the fast.ai course via the study group. But he'll be talking about those for the next EMEA meetup. The March Americas meetup is to be determined. Actually, Charles was scheduled for March, but we had a cancellation earlier in the month for our February speaker, and he graciously agreed to step up and host us for February. So we're still looking for our March speaker. But we've got also two great speakers lined up for both EMEA and Americas for April. And of course, this forum depends on your participation. So please express your interest and willingness to present a paper via our call for papers or call for presenters, which is at twimlai.com/meetupcfp. You don't need to have authored the paper. You don't need to understand every single detail about the paper. You just have to be excited about the paper and about learning, because presenting a paper is the best way to learn a paper. So I encourage you to hit that CFP and submit a proposal. So this is the part of our meetup where I open the mic up to you for your questions and comments and general community discussion. This can be on any of these topics or more. Questions or comments on recent shows on the podcast, topics that you'd like to hear more about from future guests. Thoughts on things that you're working on or that have caught your interest in news items or projects or papers that you've seen online. Anything's open. And maybe to get things started, I wanted to make sure everyone was aware of a special program that we did last night. We hosted our first ever what we're calling TWiML Live, kind of a live open panel discussion or live panel discussion that was focused on the controversial release of OpenAI's new GPT-2 language model. And if that's of interest, we can talk about that. But at this point, I want to kind of turn the mic over to you and get a sense for what you're working on and what you want to chat about. Who wants to go first?
I'll make a comment.
Yep.
That I saw recently, the video cast with Joachim's on propensity models and learning to rank. We had used Joachim's stuff years ago when I was at eBay on the search team.
Oh, really?
I thought, oh, yeah, absolutely. And he's a world expert in this stuff. And it was very, very interesting having him on and discussing these things on doing propensity models and causal modeling for search is something I'm actually working on now with a client. And I thought it was excellent.
Awesome. Awesome. Great to hear. Yeah. And we had, I think it was our last Americas meetup. We had someone presenting kind of in that same research direction on kind of bandit models and optimization using those type of models. So if you're interested in that field, the last meetup, you can find the recording for all these meetups at twimlai.com/meetup, but the last one in particular might be of interest.
Great, that's great.
Did anyone happen to catch the panel discussion last night? Fortunately for you, it is. Oh, someone was jumping in.
No, Sam, I saw the message pretty late. I would have loved to be, to join in. So I'll catch the replay.
Yep. Fortunately, the replay is up on YouTube. And if you're on Twitter, so I can maybe talk a little bit about the background here, since it doesn't sound like. Well, actually, let me ask. Independent of having seen the panel last night, has anyone on the call, been aware of the quote unquote controversy around this new language model?
Yeah, I read about. Sorry, Charles. Go ahead, Charles.
I had a client reach out to me within, I think, half a day of that being published in the news and asked me if I could do this for them.
Huh. Interesting. And so they were inspired by the possibility and not deterred by the prospect of it being too dangerous.
Well, yeah, I mean, they're not, they don't care. I mean, these things have been published before. There was a group at the University of Chicago that claimed they could do this, but then when we followed up, they hadn't released any code. So there are people claiming they can do these things. Oh, it's too dangerous. We can't release code. Does it really work? I'm not even sure it works. I mean, do they cherry pick the results? Can you do it in production? No, this is when I was at EHOW many years ago. I don't know if you guys remember EHOW. Demand media, and this was the holy grail, being able to auto create content. We were very interested in doing it, and we weren't going to do it for nefarious purposes. We were doing it to to create content that was of legitimate interest to people. So I think it's a little overblown, but yeah, they're immediately interested. Absolutely.
Yeah, interesting. So these were all of the issues that we explored on the call last night. So basically, for those, I'll try to sum it up quickly for those who haven't been catching this. Last week, OpenAI announced a new language model. It's called GPT-2. It's basically an unsupervised language model that was based on, it's kind of an extension of some work they previously published on, the GPT model. They basically crawled the web, 8 million web pages, 40 gigabytes of data, and they trained a model, a type of model called a transformer model, in an unsupervised way. And they produced this model that could be used. For those that don't know, a language model is basically a model in NLP that is used to predict the next word given some context. And if you follow the fast.ai courses or participate in the study group, we play around with language models in there. They are often done using recurrent neural nets or LSTMs, long short-term memory neural nets. But this transformer model is kind of a new approach that doesn't rely on the recurrence. And so they trained this model, and they presented. So they announced the model, but did not release the full model. The full model, it contains about 1.5 billion parameters, and instead they released the model that only had about 117 million parameters. So a much smaller version of this model, but at the same time wrote a blog post that included some, very compelling examples. The main example that they presented was they gave the model a sentence about scientists discover a herd of unicorns. And basically the claim is that this model, given only this prompt, produced I don't recall the length, but many paragraphs of coherent backstory for this made up scientific discovery. And so there was an understandable kind of outrage or firestorm, let's say, because it raises a bunch of issues. Some of the issues we talked about last night were the, releasing a model like this and making claims about being state of the art across a wide set of NLP, established NLP problems, but not releasing the model so that it can be independently verified by other researchers. There were issues raised about it only being released in the smaller model in English, or them only kind of developing it to support English and not making it available for folks in lower resourced languages to kind of advance the state of NLP in their language, which raised kind of inclusion concerns. There were concerns about the general. They kind of pre-released this or pre-announced this to journalists, and a lot of the resulting media coverage was kind of like, Terminator-esque, like, hey, OpenAI created a language model that's too dangerous to release. So there were a bunch of concerns, and we had a really interesting discussion that included representation from OpenAI on this in our TWiML Live. So I'd really encourage, if any of this piques your interest, we go into a lot more detail and flesh out a lot of the issues in that conversation. It was really, really interesting.
Cool.
Any thoughts or comments on any of that?
Is that linked to Elon Musk leaving OpenAI also, or was that independent?
Yeah, I think several have suggested links to Elon Musk's involvement in OpenAI and his general kind of AI paranoia, or at least in some of the media headlines, but I don't know, what the linkage it might be.
There are some technical issues in the paper that were interesting.
What caught your eye?
So, for example, they point out that many of the standard data sets like CFAR, which are used for evaluating neural networks, contain lots of duplicates. And that if you remove the duplicates from the data set, you see a decrease in performance by like 2%, which in this field is enormous. So they were pointing out how difficult it was. And that actually comes up quite a lot in the industrial work that I do. We have lots of data about textual data, and there's a lot of presumably human data, but there's a lot of duplicate text, and it causes a lot of headaches. So that was very interesting that they pointed that out. I don't think anyone has pointed that out yet in the scientific community, that these so-called data sets that are basically the gold standard for evaluating these models may not be as good as they seem. And of course, the point being that if you get an improvement by a few percent, you may actually be doing something like, I'm just memorizing the data. I'm doing well in the duplicates. That's not really a good test of the model.
Right.
So I thought that was something very subtle that may have been missed by, that was one of the interesting things in the paper that they wrote, because you're right. It was basically they just reused the code that they had before and made it bigger. And it was all about how they clean the data. They get this massive data set and how they cleaned it and what they did to it and how they changed the features and how they were able to get much better performance that way. And I think a lot of people maybe underestimate how difficult it is to build data sets for these systems, to train them in the real world.
Yeah, I think that comes up a lot in our conversations, how difficult that is in practice. Yeah. But yeah, the one of the comments that was made last night was, just that this was really they in some ways it's kind of presented, or the impression was was made that this was kind of a huge innovation, but really they're just kind of scaling the model that they previously built. And there's a lot of commentary. On the one, I'm gonna stop here because we covered this all on the video, and I don't want to take too much away from your time, Charles.
Okay.
So we're gonna leave it there, but again, very interesting. It's on our YouTube channel, and you can reach the video directly via the link that's on your screen. And so, without further ado, Charles Martin on his paper, Implicit Self-Regularization in Deep Neural Networks. Charles?
Okay, great. Can you see my screen?
You're going to have to hit that share. Well, I think you can. Yeah. Okay.
We're good?
I can see it. Yep.
Yes.
Okay, great. Great. So this is, let's see if I can get this, here we go. So who am I? I run a boutique consultancy that does research and product development in AI and machine learning. We've had a number of clients like BlackRock, Roche, eBay, GoDaddy. We work with private equity, and I even have a small project in alternative energy by an institute that's funded by the Page family. So in addition, so that's me. I've been doing machine learning and AI really since the late 90s. It's just a very exciting time to be in this space. This is in collaboration with Michael Mahoney. I think Michael's on the call today. Michael's a professor at UC Berkeley. He's a specialist in randomized linear algebra and scalable implicit regularization, things like this. And so he's been super helpful in just helping us get these papers out and developing these ideas. Really was updated. We sort of met at a conference a few years ago. And we had worked on these things in the 90s in statistical physics of neural networks and theoretical chemistry, and he sort of convinced me that I should take some of my spare time and do some research, and we've been doing this, and sort of this last year we've had a huge number of results. The paper, when I first talked about, was this first paper, Implicit Self-Regularization in Deep Neural Networks, Evidence from Random Matrix and Implications for Learning. You can find this on the archive. This is the long version. It's probably over 50 pages, very, very technical, sort of a pedagogic version. There's a shorter version, which is just traditional heavy-tailed self-regularization. It's about 10 pages. It's also in the archive, and we submitted this to ICML this year for 2019 ICML. We also have a couple of other papers. One is a Rethinking Generalization, which we've recently submitted to JLMR. And another one, which is Heavy-Tailed Universality, Predicts Trends and Test Accuracies. I'll talk a little bit about that also. And that's also on the archive and submitted to ICML this year. So this sort of is a large body of work. And I'm just going to kind of give you a conceptual overview of what we're doing. I'm talking a lot about code, show a lot of graphs. I'm going to avoid a lot of the heavy math unless someone's really interested in it. So let me just kind of get started with some of the motivations. So in 2017, there was a best paper at ICLR, and it was this best paper on understanding deep learning requires rethinking generalization. And what they did was they took a really large model and they randomized like 10% of the labels in the data. Some large ImageNet model, I think, something like this. And they randomized the data, the labels, and they found out that the model would always overfit. And they would try to apply regularization, and they find out they couldn't prevent the overfitting. And this led to and apparently this was a big thing. Apparently they were surprised that neural networks overfit data. And apparently this was a big idea because it seems to violate a lot of basic principles we understand theoretically about generalization. So this is sort of the first paper we wrote on this topic. And essentially what I said was, look, if you remember how regularization works, if you're a theoretical physicist, we did this stuff in the 90s. And this idea was that regularization, this overtraining, is puts you into something called a spin glass phase, meaning basically you can imagine if you had a binary classifier and you were to take some subset of the labels and randomize them. So you take in random labelings. So you form in random labelings of the data. And so this sort of red line here represents, these are sort of, I randomize these labels, or I randomize these labels, I randomize these labels. I do this n times. Or you do it for in labels. If you do this for in labels, you would get 2 to the n possible solutions, 2 to the n various possible labelings you would get out of randomizing in of the labels. This would give you 2 to the n overtrained solutions. That is, each of these represents a different solution. The neural network can overtrain to any of them. And what's interesting about this is that locally they look convex. It doesn't look like anything's wrong. You train the neural network, it doesn't look like it's getting trapped in a local minima. However, all of these solutions have really, really high barriers. So when you overtrain, you get stuck this one, you can't get over to this one. And this was known, this is sort of what we thought of overtraining from the context of statistical mechanics and theoretical physics. When you overtrain a system, what happens is, it just gets trapped in this local barrier and it can't get out. And there are all these different ways of overtraining a problem. So this was sort of our first approach to looking at this. And then we thought, well, that's nice. I mean, this is where we wrote a paper on this, a long paper. It's been very controversial. We resubmitted it this year to Journal of Machine Learning Research. But this doesn't solve another problem, which is a more bigger problem that led to us like, what is regularization in neural networks? What's going on here? If you look at a neural network, you ask, what is regularization? Everything is regularization. Every knob and switch that you can tweak or turn on or turn off is regularization. Drop out, it's called regularization. You decrease the batch size, that's a form of regularization. You add noise to the data like they did in this paper. That's a form of regularization. And I think there's a paper here I listed. There are probably 50 different things that people do to neural networks, all of which are called regularization. And so we got to thinking, well, that's kind of odd. Maybe we could say something more about this problem of rethinking regularization and generalization by thinking about what regularization really is. And so we go back to the beginning, what is regularization? It's a little bit of math. If you solve a problem like linear regression or ridge regression problem, you form WX, you have some weight matrix on some data and you get some labels. And usually you solve this is you form the correlation weight matrix of the weight matrix. And then you form what's called, and this thing is usually not invertible. So it's ill-defined, it has 0 eigenvalues. So you add something you add some parameter to the diagonal, and this is called Tikhonov regularization, or, we say, it really was developed by Phillips, but we like to say you want to make something sound fancy, you give it a Russian name called Tikhonov regularization. And this is what everybody thinks of in machine learning as traditional regularization. And if you rewrite this, it looks like your typical optimization problem. I have some loss function, I have some regularization parameter, and I'm trying to keep the norm small. So I'm trying to keep the norm from blowing up. So this is very, very standard class of regularization problems in machine learning. And the idea here is that you want to try to soften the rank of the matrix. You don't want the matrix to be full rank. You want to soften it by focusing on the eigenvalues that are larger than this regularization parameter. And I'll go into some detail. I'll give an example of this a little later. But the primary idea is you want to study the weight matrix. The regularization occurs at the weight matrix. So we thought, well, let's take a look at the weight matrices in neural networks. So in a typical neural network, we write it down. Let's just write down the energy for a deep neural network. Typically is some bias with some weight matrices and some activations. You apply the activation to the input data, then you multiply by weight matrix, you add a bias, you feed that back into another activation, you add a bias, multiply by weight matrix. You do this over and over again, you get this energy for a deep neural network. And so you typically have a loss function. And what the loss function does is it takes the sum over all the input data and it plugs it into this energy function, subtract off what your predicted label is, and you minimize that. And you minimize that by varying the weights and biases. So in this sense, we can study something called the energy landscape, meaning that we will understand how does this energy function change during this minimization process. And we're just interested in just this part of the landscape and what happens to the weight matrices. And what we know is that, look, you can write this down, you can plug this into TensorFlow or Keras, you run it, but what you want to do is avoid overtraining. This is the big problem. So the motivation here is that, we're going to study the energy landscape as it's determined by these layer weight matrices. We're going to do this, and we're going to try to characterize what is learning in deep learning. So we're going to study.
Can I jump in with a quick question?
Absolutely.
And I suggest that anyone that has questions either, you can drop them into the chat window here in Zoom, or we'll pause periodically. But when you talk about energy, are we just talking about the feed forward outputs? And is energy landscape like some kind of space formed by the outputs, the feed forward outputs, or what's the best way to think about energy? It's not a term that
I think of energy sort of just in the physics sense. The energy is just this. It's whatever this optimization function is that's formed by just the weight matrix and the parameters being pumped through the activation. So yeah, it's like the feed forward part of the network. Okay. So if you go back, and so we're going to ignore things like there's other parts of the optimization problem, like the batch size, the learning rate, parameters of the activation function. Those are all things, in particular, things you might tune, like the batch size and the learning rate, or the amount of dropout. Those are things that are sort of secondary to the energy landscape. They're parameters that affect the learning process, but they don't. They're not really part of this function. In some sense, when you run an SVM, or you run XGBoost, you wouldn't expect that modifying the learning rate is going to change your SVM results significantly. But when you modify the learning rate in a deep neural network, it goes bananas. It can totally screw it up. So that's the thing we're trying to figure out. We want to isolate just the energy landscape, and then what we'll do is we'll do things like we'll change the batch size and see what happens.
Got it.
And
any other questions?
Okay. And the tool we're going to use is we're going to look at we're going to form this correlation matrix. So we're going to just multiply W transpose times W and normalize it, and we're going to look at the eigenvalues. So I'm going to give you an example of, and we're going to use something called random matrix theory to study this, but I'm going to give you an example of what this looks like in a more common problem. If you guys have ever done something like, go ahead.
You do this for every particular layer?
We're going to do this for every weight. We're going to do this for every weight matrix, every layer weight matrix. We're going to look at all of them. And then we're going to have. And then
look at the correlation between different eigenvalues within the different layers as well.
We're going to look at we're just going to look at the correlations within the layer weight matrix itself to start off with. So we're just going to start with the simplest thing. Can we just look at the correlations on the individual layer weight matrices? And what I'll show you as we get to the end, I'll show you we can actually do things like we can predict, by doing that alone, we can predict the generalization accuracy of a neural network without peeking at the test data. We can actually predict how well the network will do just by looking at the weight matrices themselves without actually having to peek at the test data, which is somewhat of a remarkable result. So I'll just start with an example. Is everyone familiar? I hope they're familiar with something called latent semantic analysis. I thought this might be an easy example. It was something very popular, a traditional thing you would do if you have something like a term document matrix. So you're trying to cluster some documents in machine learning. You would form the TF-IDF matrix. You would do the SVD decomposition of that matrix. And then you'd use something like truncated SVD, like in scikit-learn. You can use the truncated SVD tool. And you just keep, say, the top 400 singular values. So you would form this truncated SVD of your TF-IDF matrix. And the singular values are just the diagonal parts of this matrix. And LSA essentially gives you a soft rank approximation of your TF-IDF matrix. So if people are familiar with that, I hope, as an example, this is an example of what we're going to do. Now, if you were, alternatively, you could form this correlation matrix and compute the eigenvalues. And we're going to call that the eigenvalues, we're going to call the empirical spectral density. And by that, I just mean a histogram of the eigenvalues. And the eigenvalues are the square of the singular value. So the eigenvalues, singular values, they're kind of interchangeable. And if you plot this, and this example is a little contrived, but I wanted to give you an idea of what this might look like. You might see the histogram might look something like this. You're going to have some bulk region out here, which represents things you want to throw away. When you do LSA, you throw that part away. I'm sorry? Okay. Then there's these spikes that sort of appear out here. And this is the information you want to keep. This is what you keep when you do LSA, or you do clustering, you do spectral clustering. And then there's this part here, which is this tail, this heavy tail. And in fact, you usually end up, in LSA, you end up keeping some of this. So the takeaway here is that if you look at the histogram of this thing, it's kind of heavy-tailed. It's got some part you might want to throw away that's kind of bulk. It's like bulk random. There's this part you're not really sure if it's heavy-tailed or not, because if you fit it to a power law exponent, here the power law exponent's like 4.75, so it's kind of heavy-tailed, but not too heavy-tailed. And sort of the challenge here is to figure out, you know, where the information is in this histogram and where's the random stuff you can throw away. And this is sort of a very common problem in clustering. And we're going to take a deeper look at this by applying this to a neural network. So let's say we take an example of, and this is how you do it in code. I want to show you the code. So if you were doing code, you know, let's say we have a neural network, you would load up Keras, you go to the model, you get the layers, you get the weights, then you get in and M as the shape. In is bigger than M, so it's the larger one. You form the dot product, you take the eigenvalues, and you plot a histogram. That's all we're doing. It's that simple. Now, if we do this for a neural network, we have a toy model. We'll train a small model, a 3-layer MLP on CFAR, and we'll monitor what this histogram of the eigenvalues looks like. The initial is red. So this is the singular values, and these are the eigenvalues. The singular value, this is red, the initial is red, and the final is blue. And what we find is that the initial, it's just this bulk. So if you look at the singular values here, you would just see this bulk region, and this part of the bulk can be described using traditional random matrix theory, something called Marchenko-Pasteur random matrix theory. And random matrix theory would tell you exactly that this should form this bulk. But then there are these spikes that appear out here. And these spikes contain the information. This is the information in this neural network. And if you look at the square, if you square this and you get the eigenvalues, you also get something which kind of looks like it kind of comes, it has a peak at 0, comes down here, and then there are these spikes. So we call this region here, which is sort of random, we call the bulk, and there are these parts out here that are spikes. And this is typical of what we see when we look at small neural networks, toy neural networks, you know, something like LeNet5 or something like this. If, however, you do something like you shrink the batch size. Well, for example, in the first paper, that's what we did, is we shrank the batch size. So we tried to increase the amount of self-regularization in the system by decreasing. There's a phenomenon called, I don't know if you guys know about it, it's called the generalization gap phenomenon. And what it means is that for some reason, smaller batch sizes generalize better than larger batch sizes. And that's very, very strange. Nobody knows why that happens. If you do this with any, like a typical small neural network, and you start off and you just pick some weight matrix, it starts off looking like a Gaussian random matrix. And then over time, these spikes start to pull out. And then they pull out even more. You see bulk plus spikes. Then, so most of this, then you get sort of this sort of collapse of the bulk here. Here, you see these spikes, the bulk is very crisp. There's this nice separation. Then all of a sudden you start getting a tail forming, this heavy tail. And then it gets larger as, you know, you go from batch size 50 to 32 to 16. You go down to batch size 8, it starts to pull out. You go down to 4, pretty soon the tail is, it's stopping to look like a bulk. You can't fit it to anything. This red line is a fit to random matrix theory. You can't do that anymore. And then when you go all the way down to batch size 2, where you get the best generalization, the system's totally heavy-tailed. There's no more bulk. It just becomes completely heavy-tailed. And so what we discovered is that when we train these small networks, we were looking to try to understand the generalization phenomenon. We discovered that as we decrease the batch size, that the random matrix would become heavy-tailed. And that was fairly puzzling to us. So in random matrix theory, a lot of people who do theory say, well, we're going to assume that the matrix is a Gaussian random matrix. So a Gaussian random matrix in random matrix theory, if you have a Gaussian random matrix, the theory gives you a very simple form. If you plot the histogram of the eigenvalues, depending on the aspect ratio, the shape, and the variance, here variance is 1, you get some simple form, and you always have the same sort of basic principles. The shape just depends on Q and maybe on the variance, which here is 1. The eigenvalues are always crisply bounded between some minimum and some maximum value. And notice the eigenvalues, unless Q is 1, the eigenvalues don't go to 0. They stay above 0. There are very crisp edges, so you don't see any kind of bleeding out or bulk decay at the edge. And you may see a few spikes, may appear sort of out here, you may get some spikes. So this is sort of the traditional random matrix theory that a lot of people in academics and people use. Now, having spent years doing theoretical physics, I happen to know about this other part of random matrix theory called heavy-tailed random matrix theory. And here we have, if W is heavy-tailed or is strongly correlated, then the density will also have, the histogram, the ESD will have heavy tails, meaning it's all spikes. There's no bulk. It all becomes spikes. It's all spikes, and it just decays. This is a theoretical model of what it looks like, and this is a real model. This is actually the ESD for AlexNet, and it's one of the large layer matrices in AlexNet. And you'll see that this thing becomes very heavy-tailed, and you can fit the spectral density or the ESD to a power law where it depends on this parameter negative alpha. So lambda negative alpha, you get this power law fit. And so this is the first part of the paper, goes into great detail about what we're doing. But the point is, we do this, we're going to find out all pre-trained neural networks look like this. They all look like this. They all, and this has some big implications. So we sort of came up with this, we call the 5+1 phases of training. It's a pictorial phenomenology that lets people sort of figure out and characterize your weight matrices. And we go through in the paper, describes basically, you can have something which is very random-like. And so if you fit it to Marchenko-Pasteur theory, we can provide some code that you get a fit, and it fits very nice to theory. You can have it bleeding out. It sort of bleeds out from this edge here. You can have bulk plus spikes, where you have a very clean bulk, and you have these spikes that appear, and this is where most of the information is, and this is random. You can have bulk decay, where it starts to decay at the bulk. Notice it's no longer crisp here, but it's sort of decaying. It's starting to look like a power law. And then you can have heavy-tailed. And then there are some pathological cases where you have zero eigenvalues, where you have singularities. And so this is a phenomenology, and you can relate this back to some deep ideas in random matrix theory. So it turns out there are these things called universality classes, which are different models for how random matrices should behave. And depending on the power law exponent, they all have different behavior. And the point is that each of these, and I won't go into great detail about the universality classes, but the point is there are different universality classes depending on if you're very, very heavy-tailed, or you're just kind of fat-tailed, where 2 is, you fit the power law exponent, or you're kind of weakly heavy-tailed, or you have sort of a Gaussian random matrix plus some spikes, or it's just Gaussian.
And so,
go ahead.
If I could jump in here, have you kind of introduced at a high level random matrix theory? We've been talking about it, but is it something that it's expected that folks that are doing work in deep learning know about, or is it something that folks don't really know about and it's kind of pulled over from physics and, hey, look, it kind of applies really nicely to deep neural networks?
Okay. It's the latter. It's sort of like Michael pointed out, one of his talks, we do a lot of randomized linear algebra, but we never use random matrix theory. A lot of these ideas actually come from theoretical physics and finance. So they've been developed in computational finance. I used to work at BlackRock as a quant, and we use them for modeling things like portfolios. So yeah, we've pulled these, the random matrix theory has been pulled out of theoretical physics and finance, and we wrote this huge 50-page paper to explain where all these things are. And we sort of tried to put it in a pictorial framework so you don't have to go through all the heavy math to figure out, okay, how do you use this? Mm-hmm. And each, go ahead.
So what's kind of the 30-second overview or the kind of top 3 takeaways from random matrix theory?
So the takeaways are, if you have
from necessarily, apart from your application here in deep learning.
So if you have just a simple Gaussian random matrix, and random matrix theory tells you something about what the shape of the histogram looks like of eigenvalues. It tells you the shape. It tells you what the fluctuations are like at the edge. So it tells you whether it's, in other words, it tells you that the eigenvalues have the distribution has this shape. It tells you that there are fluctuations at the edge that can be very, very crisp. And it may tell you something about the spikes that appear out here. It can make predictions about what the spikes will be.
And outside of deep learning, that's typically used to tell you what?
It's used for things like signal to noise, like doing signal to noise detection.
Okay.
So if you're doing, go ahead.
So this is really cool. So I guess you're making the argument that as you go from like a very well-defined probability distribution of your eigenvalues to something that is long-tailed, then you're going to be more generalizable. For
yes. Yes.
And let me finally. Yes. You could use convolutional. You could actually use another learner to look at the distribution of your weights as you're training it to say, we're done because this model should generalize pretty well based upon what we understand from how other models, the distributions of eigenvalues look.
Maybe. So I'm going to show you now. The other takeaway is this: is that there are these universality classes, and this idea that when you see power law exponents that are all within a certain range, that's special. That means that there's some underlying mechanism driving the system. This is an idea from statistical physics in quantum field theory. That when you see, if you do a bunch of experiments, and you measure your power law exponent, which is this this exponent here, how fast it decays. And if you see that they all lie within a certain range, and you're a theoretical physicist, you start jumping up and down because you realize there's something special going on here. So I'm going to show you that. So the next part of this
you
is
can also
that,
relate it to, I guess, entropy, right?
yes, yeah, we do that as well in the paper. We relate it to things like the soft rank, various measures of rank. It turns out, now what I do here is, in this part, I'm going to apply it. And what we do is we do something that we haven't found anybody else do. We analyze pre-trained neural networks. You know, I work in industry. I don't train. I have people call me, a client calls me up, what will it take to retrain GP2? Well, I'm going to need $50,000 to retrain it. Okay, thank you very much. So, you know, we use pre-trained neural networks. So it seemed to me we should analyze the weight matrices of pre-trained neural networks. So this solves a couple of problems. One, I'm not spending 6 months trying to train a network. Two, I can look at things that are production quality. And three, everything is 100% reproducible because you can just download the network and just redo what we did. So everything I'm showing you, we even wrote a tool called Weight Watcher. And you can download you go pip install Weight Watcher, and it will reproduce all these results for you. At least the ones are going to be later. So it's completely, all, you know, this idea that science is not reproducible, that's crazy. Yeah, how would you? So I'm going to show you some experiments we've done. We dug in to some of these pre-trained models. We had to retrain Lynette 5 from scratch. I couldn't find a version of it. So Lynette 5 is the first model developed by Weekon. It's convolutional layer max pool, fully connected. We looked at AlexNet. We looked at Inception, ResNet, DenseNet, on and on and on. I've looked at probably 50 different pre-trained neural networks, and I've looked at over 10,000 weight matrices. I'm going to show you what the results look like, and across different architectures, both for image processing and for natural language processing. If you look at Lynette 5, well, you get bulk plus spikes. You get something very simple. The rank or the entropy, the soft rank is like 10%. You lose 10% of the rank. It's mostly this bulk region described by traditional Gaussian random matrix theory, and there are some spikes here. And we find that all small toy models that people do look like this. So I don't like toy models. You look at AlexNet. AlexNet, looks like it's heavy-tailed. We try to do a fit to the theory. If you use the Gaussian random matrix, Marchika-Pasteur theory, you can get a fit, but you still get this sort of bulk collapse. And if you zoom in, this is FC1, I think this is FC2. If you zoom in on some of these, you see that the fit is just, you miss all this Frobenius mass up here. So we sort of a bulk decay. You're starting to see heavy tail. You look at Inception. This is one of the, we had to dig out Inception, this weight matrix. If you know anything about Inception, which is this weight matrix in the middle of the model, which I think is used for, if I remember correctly, for residual connections. And it sort of has this bimodal structure. It looks almost heavy-tailed. You can try to fit it to random matrix theory with this red fit, but it just doesn't. You know, you'll see the onset of heavy tails. And the other thing we found is that very rarely, when Q is greater than 1, you should never see 0 eigenvalues. So Q is the aspect ratio. It's the width to the height of the matrix. And so whenever our theory predicts that whenever Q is greater than 1, you shouldn't see a lot of 0 eigenvalues. So not only should you see heavy tails, but you shouldn't see 0 eigenvalues in a well-trained model. And so that actually, it turned out there's other people doing things like on general adversarial networks who observe the same thing. And so when you see this, this will signify over-regularization. You did too much. The weight, you killed your, you killed all your eigenvalues, and now you've got a singular matrix. So I'll skip this part. This is sort of the idea is that you look at all these different models: AlexNet, VGG, ResNet, Inception, DisNet. We always see this sort of heavy-tailed self-regularization, and it resembles what we saw when we shrank the batch size. So when you shrink the batch size, you see this, but when you, these are trained on normal batch sizes. Now we looked at thousands of these. I tried to find every neural network I could find that was pre-trained. If you look at all the image nets, you find if you fit the power law exponent, you find 80 to 90% of them live between 2 and 4. So this for example, is a plot of the, these are the linear layers. So these are the linear layers. If you look at the linear layers, you see this, you see a couple outliers. If you do it for the Allen NLP models, the 6 models for Allen NLP, you also see the bulk between 2 and 4 and some outliers. So if you do it for the, we take the 2-dimensional, if you take the convolutional 2D layers and you pull out the feature maps and you treat them like weight matrices and you fit them, you'll get power law exponents. This is 7,500 weight matrices for all the ImageNet models I could find, and in the paper we go through all of them. And 80 to 90% of them have a power law exponent in here, less than 4. So between like 1.8, 1.9 to 4. And there are some technical details with but there's some technical details in fitting these things, but it appears that you have something universal. You have power law exponents in this. Recall I said when the power law exponents are in a certain range, that suggests something. It suggests that there's something underlying, there's some underlying mechanism driving this. So we've observed this in nearly every weight matrix you see. I think and we very rarely see rank collapse. We almost never see any 0 eigenvalues. So if you look for 0 eigenvalues, there's maybe very, very small eigenvalues. There's, of all the PyTorch models we could find in the linear layers, there's maybe one very small eigenvalue, and none of the Allen NLP models showed any 0 eigenvalues. The exception to this is BERT. If you guys know what BERT is, the pre-trained model from Google that predates his GP2 stuff, we actually do see that BERT is actually kind of different. So there's always an example. BERT has 5,400 layers we had to look at, and we didn't see as much universality in BERT, which is kind of interesting. We don't know what's going on there, but so we, it works, but not all the time. In fact, what we think is that BERT may in fact be just too big. It's just it has way too much capacity for what they're doing, and you could probably shrink it down. There's been a lot of work doing things like optimizing VGG. I mean, there's been 5 years of optimizing the VGG models, and these NLP models are really really coming out this year. So we think there's a lot of room for improvement. Now, the last part of this is this idea that because the power law exponents are universal, there's some underlying mechanism. So we're going to do something kind of crazy. We're going to suggest that if I were to take the average power law. So if I just take the average, imagine I took I measure all the power law exponents in a weight matrix, and I took a weighted average, where the weights are somehow related to the scale of the matrix. This suggests that smaller, and when alpha is smaller, this alpha hat is smaller, you generalize better. So because if you see power law exponents, and you're seeing that when you decrease the batch size, they get smaller, it suggests that on average, smaller power law exponents should tell you that you generalize better. Remember, we're not looking at the test data. This is just some crazy hypothesis I have. So it turns out, if you plot them, it's true. If you plot a weighted average, and if we want to go through the details, we got about 10 minutes, so I don't want to, we could go back through that. But the idea is if you plot a weighted average of these power law exponents versus the test accuracy, and you look at like a class of models, like you look at VGG 11, 13, 16, 19, and for the VGG and the VGG with batch normalization, you get this amazing straight line. Test accuracy, weighted alpha. This is literally, and this is literally right out of the box. If you do this for ResNet, all the ResNet, I tried to find every ResNet model, 10, 12, 14, 16, 18, all these different models that are optimized for mobile networks, all the way up to 152, and you plot average alpha versus the test error accuracy. Again, you see this sort of correlated trend going down. There may be a couple of outliers, but even the outliers are kind of in the trend. You see this amazing trend. And we've done this for a wide class of deep neural network architectures, and we find the trends are all pretty good. Now, there are very few that have as many as VGG and ResNet. There are always some exceptions. And we even wrote a tool called Weight Watcher. And what Weight Watcher does, you say pip install Weight Watcher, and you give it a model in Keras or PyTorch, and it will actually produce these ESDs for you, and it will produce this weighted alpha. And there's a fast version and a slow version, but you can just reproduce these plots directly. And the reason this works, there's actually so we have a few minutes. There's actually a more subtle reason. It turns out that there was a paper that came out of Google, Google X, that was discussing if you measure the average, if you measure the capacity as a product norm, that the capacity of a neural network as a product norm seems to be a good measure of a data-dependent VC-like capacity metric, meaning that the product norm seems to be correlated with the test accuracy. But in order to do that, they ran these toy models, and they had to modify the cross entropy loss. I said, I don't want to do all that. This should work out of the box. If you take the log of the product norm, take a log of a product, you get a sum. And so we notice that the average product norm, the log of the product norm, is basically an average of the log norms. So it turns out, if you just take the average log norm of your weight matrices, it actually works pretty well to generate the test accuracy. And I don't think anyone's pointed this out. So this is actually really, really fast and can be applied to very, very small matrices without too much error. I mean, it's not perfect, not as good. Our model, by the way, Weight Watcher supports that as well. If you do the weighted alpha, we think you get a little better accuracy, but it's slower because you have to do all these eigenvalue calculations. And we even have an example of, if we go through the math, I won't go through this. I'm just going to point out that we can derive a relation. So we have in this new paper, we sort of derive what Michael calls a level of physics rigor, which means it's not, which I think he means it's not rigorous, but it's a level of physics rigor where you can show that the log of the Frobenius norm squared is approximately equal to alpha times the log of the maximum eigenvalue of your weight matrix. So that's our weighting factor. So if you form alpha, and you form it as alpha is some average over the maximum eigenvalue of your weight matrix times the parallel exponents, and you use that as a capacity metric, and you either use the linear matrix or the two-dimensional feature maps from a convolutional layer, you can actually predict test accuracies without having to peek at the test data. So we think this would be very useful for things like AutoML. If you're trying to do AutoML and you're worried about peeking at the test data over and over again because you might overtrain when you do AutoML, we think this might work useful. Or if you're doing fine tuning and you're trying to fine tune some neural network based on some pre-trained model, and when you do fine tuning, you don't have a lot of test data. You may only have a few hundred examples to fine tune. Then this might be something you could use to help you try to fine tune a neural network without having to constantly peek at the test data to see if the parameters are right. So that's sort of the gist of it. I think that ends the hour. I didn't want to run over the hour, but we can definitely go into details, whatever you guys want to go into. We've published a ton of stuff on this, and I'm happy to answer any questions you might have.
So you can only apply this from task to task, right? You can't use your alpha or these metrics to compare the performance from different tasks, I suppose. Or it has to be obviously related to that.
Well, we've compared different architectures, and if you look, we compare ResNet. So ResNet is, we looked at all the different ResNets. So I mean, this is a very, very wide class of architectures. So I think it could be played across architectures. I'm not sure what you mean by task, though. Do you mean like different data sets?
Like an alpha. Well, what I'm saying is, I guess the alpha doesn't really have a absolute value. It's all going to be normalized relative to the task you're trying to solve, right? For instance, an alpha in one particular. Okay.
Right. It doesn't appear. It doesn't depend on. It doesn't seem to depend on the neural network architecture. That is on the variations of the architecture, but it does depend on the data, from what we can tell. I haven't tried looking at different data sets and comparing it.
Do you have a feeling for what the minimum, like from your theory, what the minimum alpha that one could approach?
It depends on the normalization. So you see here, you can even get negative alphas, and that's because you have to be careful how you normalize the matrices and what the internal variance is. So, you know, the minimum is, I don't have an idea of the minimum. I just do want to point out though that it appears to be less than 0 because we're taking the log. The alpha includes the log lambda max, and this number can be less than 1 when depending on what the normalization is of your weight matrices. But in terms of
finally, have you thought about?
Go ahead.
Have you thought about using, for instance, because you're training these different models, and one thing people like to do is do ensembles. Could you imagine using these alphas to help guide you? How would you ensemble these particular networks?
I haven't thought about that.
Weighting.
Yeah, maybe. I mean, that could be like, maybe you want to weight ensembles with smaller alpha. You want to weight them less. That's an excellent idea. I hadn't thought of that. I don't know. This is all very researchy, so you know, you try it out and see what happens. I mean, I'm somewhat amazed that this worked. So, all right, thank you.
So I had a question about, it looked like in the math, you're making these calculations on a layer by layer basis, but in the results you're presenting kind of at the architecture level. How do you reconcile those two?
Okay. So we do layer by layer, and then we take an average.
Okay.
So the average is related to this idea, like when you do a product norm, you measure the norm of each weight matrix, and then you take the product. So I just take the logarithm of that, and it gives me an average. That's basically the idea. And I'm somewhat amazed that it works. You know, I didn't expect. I was just kind of guessing, like, well, smaller alpha on average to give you better generalization accuracy. And then I got this plot. I was like, oh my goodness, this works incredibly well. So I'm somewhat puzzled by it. But yeah, it's because we're playing a lot of little mathematical tricks here. You know, this isn't in order to get these equations.
Right. And have you looked at, or do you think there's some kind of relationship in like higher order moments of these layers? Like if there's, one architecture has a higher degree of variation layer to layer in these values, does that, would that impact your model, or is there something you could gain from exploring that?
I don't know. When I was first doing this, I was thinking about doing like cross layer correlations. So the idea here is that these are strongly correlated systems, and strongly correlated systems look as if they're heavy-tailed. They're not really. Like if you look at W itself is not really heavy-tailed. Its spectrum looks heavy-tailed, but it itself is not heavy-tailed. So this is sort of this idea that there are these universality classes of heavy-tailed systems, and things that are, when W has a very, very large element, it will be heavy-tailed. But it doesn't necessarily have to have a large element to be heavy-tailed. So yeah, it could have a very large number of moments, and so the W matrix may have a large number of moments, and yeah, that could contribute to it being very, very heavy-tailed, and that might be easier to characterize. Doing these parallel fits is actually kind of tricky. And if you could characterize it by the moments of the weight matrix itself, yeah, that could be quite useful. Does that answer the question?
Yeah.
Okay, cool.
Any other questions? Comments, thoughts, observations? Cool. Well, Charles, thanks so much for presenting this. Really interesting work.
Hey, thanks for having me. And we really just encourage anyone to just, if you want to try it, just pip install Weight Watcher, give it a shot. And if you're a bit of a math nerd like me, you can read through 100 pages of papers and, give me a hard time, send me an email and give me a hard time, and I'd be fine to answer whatever questions you have.
If nothing else, I love the name.
Yeah, well, that was the best part of the whole thing, Weight Watcher. So I'm waiting for I haven't got the cease and desist letter yet.
Awesome.
All right, thanks a lot, guys.
All right, thanks, everyone. Good night.
Good night.